We are now going to look at how we can interpret the effect that an explanatory variable has on our multi-category response through the use of odds ratios. To help understand the process, let's take a look back at how we did something very similar with a logistic regression model. So with our logistic regression model, essentially what we were doing was modeling the log odds of a success. Now, if one wanted to, one could actually interpret the odds part of that as the odds of a success versus a failure. When I introduced this, I didn't do it at that time because we only had a binary response. Either we had a success or a failure. So you didn't necessarily need to have that extra part about versus a failure. Now here's our multinomial regression model, and notice how we're also modeling something very similar. And in fact, what we're modeling is the log odds of a category J response versus a category 1 response. So we're essentially doing the same kind of thing here, but now we do need to add this extra part here to say, well, what are we making the comparison to when we have category J to begin with? So, since we're modeling again the log odds, we can now use odds ratios to help interpret the explanatory variable relative to our multi-category response variable. To look into this in more detail, let's consider a simplified multinomial regression model where we only have x as the explanatory variable. Then if I wanted to, I could apply the exponential transformation to both sides of this equation so that now we have just the odds of category J versus category 1 on the left side, and then we have the exponential function of beta sub j0 plus beta sub j1 times x on the right side. And similar to what we did for a logistic regression model, how about we look at the odds ratio now for a C unit increase in x. So here's my odds for a C unit increase in x. Here's my odds just for x itself. And look at what happens. Certain things cancel out, and we're left with the exponential function evaluated at C times beta j1. There's my odds ratio to interpret the effect that x has on our multi-category response when I'm looking at category J versus category 1. So then we can apply the same kinds of interpretations that we had before with this slight modification. The odds of a category J versus a category 1 response are the exponential function evaluated at C times beta j1 times as large for a C unit increase in x. Or we could also say the odds of a category J versus a category 1 response changed by this odds ratio times for every C unit increase in x. Well, what if though we want to do this comparison, this odds for something other than comparing to category 1? Well, based upon what we've learned before, we can simply rewrite our model so that we can actually compare any categories. And so let's say I have category J and category J prime, just to be very general. Our odds ratio then becomes this, the exponential function evaluated at C times beta sub j1 minus beta sub j prime 1. Where does this come from? Well, just simply rewriting our model. And we've already looked at an example before where j was equal to 2 and j prime was equal to 3. Okay. Some notes here. We've already essentially talked about note number 1. Now, when there is more than one explanatory variable, we need to add a statement such as, well, holding the other variables in the model constant. And also, if we had, let's say, interaction terms, if we had transformations like an x squared in our model, how do we interpret that? Essentially, go back to what you saw in chapter 2 and apply it in this particular situation. On tests and other graded items for my course, I will sometimes actually put a problem on it that says, okay, derive the the odds ratio where I have x1, x2, and their interaction in the model. Derive it, tell me how to interpret it. Inference methods, well, similar to what we've seen before. So let's go ahead and take a look at an example to apply these ideas. We're going to go back to the wheat kernel example. Now remember, with this wheat kernel example, we had a variable called class, which corresponds to soft red winter wheat, hard red winter wheat. Since that then we end up working with a binary variable, we can only use c equal 1 for that particular case. But for the other variables like density, like weight, we need to decide what an appropriate c should be. This is a particular situation where one could talk to the researcher to ask them, well, what would you want to use for c? But let's give an example of what can one do if we didn't have access to that researcher who actually collected the data. What should you use for c? Well, one option would be to, let's say, use one standard deviation. That seems like a reasonable thing to do. It would be a reasonable value to use in the context of a particular variable, one standard deviation. And so that's what I'm going to show how to do here in a very general manner. Excuse me. So let me jump on over here to 10. Okay. So I need to find the standard deviations for basically, I believe it's 5 different variables in my data set. The density, the weight, and so on. Since I want to repeat the same thing over and over again for each of the variables, each of the explanatory variables, I'm going to use a function called apply to help me do it. Okay? And let me actually copy and paste some code outside of 10 to help illustrate this process. Oops. So here's my wheat data frame, and again I want to find the standard deviation of these 5 different variables. And so what I can do to just only look at the data frame relative to these 5 variables is to say, in the column part of designating a particular set of columns or rows to actually look at, in the column part I can say negative and then combine together 1 and 7. Well, previously we've seen stuff like this, where, oops, actually I did it wrong, excuse me, where I say I want to look at columns 2 through 6. One could do that, but just to illustrate a different way to go about doing this, what I could say is negative combined together 1 and 7. And what that negative tells R is that exclude column 1, column 7. So now I have a version of my data frame which doesn't include class, doesn't include type. It can't calculate a standard deviation of some kind of character variable. That's why I'm doing this. So then in the apply function itself, I say, well, what do I want to calculate the standard deviation of? Now remember, I want to calculate the standard deviation for the 5 variables. In other words, the 5 columns that are in the wheat data frame. And so if I specify margin equal 2, that tells R I want to work with the columns. If I were to put margin equal 1, that says I want to work with the with the rows. And then apply applies a particular function to each column. I want to apply the SD function, which is standard deviation. I'm going to put the results into sd.wheat, and this is what we get. There are my standard deviations. So I'm going to create a vector called c.value that has all of my corresponding c values that I'm going to use for my odds ratios. I'm going to find an odds ratio for the class variable, odds ratio for density, odds ratio for hardness, and so on. And actually I'm going to do it kind of in a simultaneous manner. That's why I'm going to put these c values together into a vector called c.value. Okay. Now we need to find the walled confidence intervals, because remember, there isn't an easy way to do a profile likelihood ratio interval with these kinds of models. And so first of all, let's take a look at what the beta hats are. Now normally, well, I shouldn't say normally, but with the GLM function, when we got results, when we put the results into mod.fit, we would say mod.fit $coefficients to extract out the beta hats, the estimated regression parameters. Can't do that here. Unfortunately, the author of multinomial function did not set it up so that that would work. Instead, it is set up though to use a particular function called coefficients, and that will extract all of my beta hats that I need. Now, if we take a look at that again, notice I have 2 rows of beta hats. This corresponds to my beta hat 2s. This corresponds to my beta hat 3s. So for example, this is beta hat 2, 1, beta hat 3, 2. And essentially what I need to do to find these odds ratios, I need to use the exponential function with each of these beta hats. So to help do this, I'm going to pull out all the results from coefficients, just the first row, and all the beta hats except for the intercept term. So let me go ahead and do that. I'm going to do that for the when j is equal to 2, so this would be the scab versus healthy comparison. I'm going to do this also for j equal 3 for the sprout versus healthy comparison. And there's what they look like. Now all I need to do is apply the exp function correctly. Beta hat 2 essentially is a vector. C dot value is a vector, and they both have the exact same length. So when I say C dot value asterisk beta hat 2, what R is going to do is match up the first value in C dot value, which would correspond to the C for the class variable, match that up with the beta hat corresponding to the class variable. Do that multiplication. Same thing's going to happen for density. Same thing's going to happen for the other explanatory variables. I'm going to then apply the exponential function with this and nicely round it to 2 decimal places. And here are my corresponding estimated odds ratios. Of course, I might want to invert those odds ratios, so let's go ahead and do that. Alternatively, of course, I could have just simply put a negative there instead and done the inversion that way too. Okay, so let me come on back over here to my Word document. And so I do this also with the beta dot hat 3 as well. And here are some nice interpretations. Just a second here. Let's focus in on density. Okay. These are for j equal 2 to j equal 1. The estimated odds of a scab versus a healthy response are 0.06 times as large for a 0.13 increase in the density, holding the other variables constant. Equivalently, we can also say the odds of a scab versus a healthy response are 17.04 times as large for a 0.13 decrease in the density, holding the other variables constant. That 0.13 is the 1 standard deviation. So what we have here, what this is saying for us then is that we're more likely to have a scab kernel when the density goes down. Think about that in terms of that parallel coordinate plot that we saw before. Remember how we had all those scab kernels that tended to have lower densities. This is why we end up with this interpretation here for the estimated odds ratio for density. Now one could also look at the same kind of estimated odds ratio for sprout versus healthy for density as well. Please see that on your own. And you could look at other particular explanatory variables too. Again, please see that on your own. We'll relate these odds ratios back to what we saw with that parallel coordinate plot. Okay. So we've compared sprout to density. I'm sorry, sprout to healthy. We've compared scab to healthy. Well, what about sprout versus scab? I guess I already had that written there. How could we do that? Well, there are two ways. Method number one, simply apply what we see up here. This is the kind of odds ratios that we want. Now, instead for us, we need to work within the estimated odds ratios. Remember how beta dot hat 2 would contain then the j equal 2 beta hats, comparing j equal 2 to j equal 1. And if I subtract, this is in my R code, subtract beta dot hat, actually I should do a 3 there. So take beta dot hat 3 minus beta hat 2, take that times the corresponding C value, use the exponential function with that, I get my estimated odds ratios. Try that on your own. A second way then would be to change the type variable in terms of the levels, the ordering of the levels. Re-estimate then the model with this new change, and then you will have just one beta hat that you could use to allow you to do this sprout versus scab comparison. What about confidence intervals? Well, one way to do these confidence intervals is to use the conf_int function. Let me actually come on over here to 10 to help demonstrate that. Okay. So if I use the conf_int function, my model fits in mod.fit, 95% interval, put the results into conf.beta, and if we take a look at that closely, what I have here are confidence intervals corresponding to the betas. So for example, here's the confidence interval, negative 27.7 to negative 15.49. Let me actually come back over here to Word so I can write on this. Here's the confidence interval for beta 2, 2, negative 15.49, negative 27.7. Okay, so once I have that confidence interval, if I want to now work with that confidence interval to find the confidence interval for the odds ratio, all I need to do is use the exp function, where I take the corresponding value of C, I believe it was 0.13 for density, take it times negative 27.7. That's less than the odds ratio, which is less than exp, the C times negative 15.49. There's my corresponding confidence interval. Let's look at how we can do this in a little bit easier manner than in R. Okay. Now, the way that these results are stored is actually in a three-dimensional array, meaning I have rows, I have columns, and then I have a third dimension corresponding to what you would say strata or layers, and that just divides up. Are we talking about j equal 2 or j equal 3? So if I wanted to, what I could do is just, let's say, extract just this part of this three-dimensional array. So I need to work with row 2 to row 7, column 1, column 2, strata 1. In other words, conf.beta bracket 2:7. I want columns 1 and 2, and now the third dimension, that's where I put the strata. And there we go. So now once I have that, then I can multiply then each of those rows by its corresponding C value, and R correctly matches up the order of the rows with the corresponding C values. You can try that on your own. It's often good to do that just to verify that indeed that R is doing the calculation exactly as you want. So for example, with the density here, if I take 0.13 times negative 27.7, I get negative 3.6. Okay. Then to find the corresponding odds ratios, the confidence intervals, I applied then the exp function. So let me go ahead and do that. And here are the odds ratios for, this would be scab versus healthy in that particular case. Let me come back over here to Word. So here is scab versus healthy. And then we could also invert it if we want to. Then we also have sprout versus healthy. Okay. Now let's do some interpretation here. With 95% confidence, the odds of a scab instead of a healthy response are 7.64 to 38 times as large when the density is increased by 0.13, holding the other variables constant. So let's find the 7.64 here. There we go. So I had inverted the odds ratio, just like what we had done previously with the estimated odds ratio. And we get, again, that particular value there. Notice how I ended up also saying holding the other variables constant. We could also look at the same kind of odds ratio for the confidence interval for sprout versus healthy, 3.57 to 14.82 for a 0.13 decrease in density. Now let's take a look at these confidence intervals. Which ones do not contain 1? The density, the weight, and let me come on down here, density again, hardness. So these are the only times then where we have actually been able to show, given all the other variables are in the model, that that there is some kind of relationship between the explanatory variable and our multi-category response. So we can see definitely density is very important. Also, we see that hardness is important for the sprout versus healthy. Weight is important for scab versus healthy. Well, what about sprout versus scab? Well, we could do that too. Remember when we did the estimate odds ratio, I gave you, let's say, 2 different options about how to go about doing that. In this particular case, probably the easiest thing to do is that option 2, where you simply change the ordering of the levels in factor. You change the ordering of the levels in the type variable by using the factor function and re-estimate the model, and then you can almost essentially automatically get the confidence intervals based upon the code that I've shown you. Try that on your own. Okay. Now, this calculation process here, does take some steps. There are less steps involved in calculating the estimated odds ratios and also the corresponding confidence intervals through using the EM means function. And as you see here, I say the process can be simplified. Yes, it is more simple in the end if you understand then the corresponding code that's involved. But as I've said before, the code corresponding to EM means can be quite kind of quirky, and this is again another example of that. Let's take a look at the process. So I'm going to put my results into calc.est, and I use the EM means function to begin with. I put the results from my model fit in the object argument, and then we have the specs argument. And we saw this once before when we were finding the estimated probability of having category J. After the tilde, we actually have to put the response variable, which is different from what we had with GLM when we were using the GLM function for the logistic regression. Now, since we're also going to be, let's say, interested in odds ratio for, let's say, just one of our explanatory variables right now, let's say density, I have to also put density. Then for the mode, before we had, I believe it was prob, for we wanted to find probability. Now we have to use a different argument value called latent, Basically, this simply tells you, it means, okay, now you want to work with essentially the log odds. Kind of a strange reason why it would be called latent, but that's just the way it is. And now, similar to what we had when we were working with logistic regression models and EM means, when we had that continuous explanatory variable, we needed to specify essentially two numerical values that was separated by the value of C. And that's what we do here. So we say at equal, we use a list, density equal, let's say 1.25 and 1.25 plus that one standard deviation value. I could have used some other value in there for 1.25. I just chose that because I knew it was in the range of the possible density values. But you could have used actually something else and still got it right, or get the calculations right. The key is you need to use the correct value of C there. So I get the results, and then I'm going to do this a little bit the longer way. I'm going to create an object called test.info where I use the contrast function, and I put in there calc.s. And here's a new, a new argument for us, interaction. How this is used is as follows. We have a type variable, we had a density variable, and we're going to actually show results based upon both of them. And so we need some way of saying what kinds of results do we want to use. Well, we want, let's say, pairwise comparisons. I want to compare scab to healthy. I want to compare sprout to healthy, and so on. And I'm going to first say reverse pairwise, or rev pairwise. This is going to correspond to the first variable there, type. What that's going to tell R is, okay, rather than putting healthy first in our comparisons, we are going to put healthy last. So we get scab versus healthy, sprout versus healthy, and sprout versus scab. Notice it's how kind of a reverse alphabetical order than what would actually be done otherwise. Try just pairwise there, and you'll see what I mean if that's not totally clear. Then for the second element here, I need pairwise. What that's going to tell R is that I want pairwise comparisons between 1.25 and that 1.25 plus 0.13. So that's why you see density pairwise there. So notice this says, okay, I'm going to compare in my numerator, I'm going to have a density value of 1.25 when I do the odds. And then my denominator odds, I'm going to have 1.38. So next, confident. I want to find then the corresponding confidence intervals. So I put the results of test.info there. I need to again specify a degrees of freedom of infinity because for some reason this function will use a t-distribution rather than a standard normal, as should be used when we have a walled confidence interval. And if I say type equal response, confidence level 0.95, finally I get my walled confidence intervals. Compare these to what we had before, and you'll see that they match up. So again, this is somewhat simpler than what we did before, but you have to get through the quirkiness of it to make sure that you get the calculations done correctly. Okay, so I have some comments here. I think I've already discussed them all. In fact, I have, so that's great. So that was an introduction then to how to use odds ratios to interpret the effect that an explanatory variable has on the multi-category response when we're working with multinomial regression models.